Hello and welcome to Gardening at 58 North. So this video here is going to be a little bit different to my normal gardening related videos. This is actually going to be about my parents' house here, and they've basically got a house which is pretty much self-sufficient in energy for powering the house and heating the house. So one of the major aspects of the power system on the house is the solar panels here. As you can see, it's quite a large array. It's actually a 4 kilowatt array, so at peak output we can get 4 kilowatts. And it does actually produce that. We see that in summertime, it quite reliably does produce 4 kilowatts of power. In the winter, like today, the maximum is about 1.7, but the days are very short here and the sun's at a bad angle, so it really only gets that 1.7 kilowatts for a couple of hours on a sunny day. Generally in winter we get very little solar, but the solar panels here went for our monocrystalline gallium arsenide solar panels. So the reason we went for them is there's lots of different benefits. One of the downsides though is they're a lot more expensive than your average solar panel. So most cheap solar panels are what they call polycrystalline silicon panels. They're a lot cheaper because the silicon is lots of little crystals. It doesn't need to have as much wastage, and also they can use a less pure silicon, whereas here you can see each square is actually one large crystal of silicon, and you can see just lots of little fine wires going over the surface. So these cost a lot more because of that, and also the gallium arsenide adds a bit of the expense to it. So the advantages of that is because it's monocrystalline, it's actually a lot more efficient, so we can produce a lot more power. Also the gallium arsenide chemistry is the most efficient chemistry pretty much. I think there's some slightly more efficient ones, but they're not generally used for homes. They're maybe used for very specialist kind of situations. So it's very efficient, so we can get a lot of power out of a smaller area, which is useful because then we can have other parts of the roof used for other things. It also looks quite nice because you can see it's a lot darker. They're pretty much black, whereas the polycrystalline ones, normally, because they've got lots of little crystals, they reflect some more of the light, and so they're not as efficient and they don't look as dark. Another nice benefit of it is it works really low at low power and low light levels. So with a polycrystalline system, the issue is when it's low light levels, you get a lot of loss of power. The voltage is quite low, so if you only got low light system, you'll have no power until the sun comes up a bit more, and then the voltage is high enough for the inverter to work. Whereas with this system, with the voltage being higher at low light levels, the system works quite well. The voltage is high enough that even with low light you can get power into the inverter. And the other thing with gallium arsenide is the longevity is really, really good. So it doesn't degrade as easily as silicon, and you'll get much as the pure silicon ones, so you'll get a lot more life out of your solar panels. So these are rated, I think, 25-year warranty, and they shouldn't drop much power from that. So after 25 years we should be getting something like 90% of the power we're getting when it was brand new. So the solar panels should last quite a few years. As I say, 25-year guarantee is what they've got on the solar panels. So going along to the other part of the roof, what we've got here is the solar thermal system. So this is a lot smaller, and this doesn't create electricity from the sunshine. What this does is it captures the warmth from the sun, and then you can see on the right hand side there's a couple of pipes. Now these pipes take the hot water that gets heated up by the sun and pump it into the hot water tank system. So what happens is the cold water enters the bottom, the sun shines through the clear opaque surface on the top of the board. Underneath that is, at the back of it, we can't see because it's covered, is a very dark absorbing material that absorbs as much light as possible, and then just in front of that is the copper pipes that heat up and transfer the heat from the black back pipe plate to the water, and then it comes out of this top pipe here and is pumped into the hot water tank. So this doesn't really work in winter here in Scotland. The sun's too weak, temperature difference is too great. These are insulated though, so even if the temperature outside is quite low, you can still get a good temperature. So you could have it 5 or 10 degrees outside, but you can still get up to 40 or 50 degrees with the hot water. So in summertime this actually provides more than enough hot water needs for the house system, but in winter it doesn't do much. So this is basically just an extra top-up system, so that in the middle of summer we don't need to be heating the water with electricity or with fuel either, so we don't have to burn the fire and get the house too hot. We can just use this to heat up the water. Now with the new system we can actually use electricity as well from the solar panels and from the Tesla Powerwall, and from something called an immersion switch, which diverts excess power into the hot water. So this has become a slightly redundant system now. It still operates, it still works, but it's not necessary, as we can actually get power from the electric solar panels into the hot water. But it just acts as another thing to add some more heat input into the system, and it means that we don't have to take as much power from the electric system to heat up the hot water as we otherwise would. So we can get quite a lot of hot water in warm summer days when there's lots of sunshine. So one of the main new components of the system is this new Tesla Powerwall. It was actually only installed yesterday, so we haven't had it running for too long. But today's a good day to test it, as it has been very sunny, although it is January, so the production is really quite low. Normally our solar panels can output 4 kilowatts quite easily in the summertime, but at the moment it's only producing about 1.5 kilowatts. So the charging rate's quite slow. Well, the Tesla Powerwall is basically a big giant battery. It can store up to 13.5 kilowatt hours of power. This morning it was completely flat, but it's been charging up nicely. And I can show you the app now and show you how it's doing at the moment. So you can see here, we're currently drawing 1.6 kilowatts from the solar. 200 watts is going to the house, and 1.4 kilowatts is going to the Tesla Powerwall. I can click on these and have a look at other options as well. So you can see something there briefly went on. You had to pull a tiny bit from the grid, but sometimes there's maybe a 2 or 3 second delay before the Powerwall kicks in, starts delivering power back into the house. So any excess power that we used to get, what happened is it would actually get sent back into the grid, but now any excess power gets stored in the battery. I can go back and have a look at how much is currently in it. So there's only 6% at the moment, which is very low, but it will be increasing as the day goes on. So what I'll do now is I'll go put a heater on. What that will do is draw more power into the home. The solar won't be able to produce enough power to keep the heater going. So what it will do is then power will start being delivered from the Powerwall into the house. That way we don't need to dip into the grid unless the Powerwall's completely run out of power. So I've got into this room now to show you what it looks like when it starts to draw more power. So as you can see, so there's 2.5 kilowatts being used by the house because I put this heater on, and that's now drawing 1.5 kilowatts from the solar, and then any other power that's needed is being brought out of the Powerwall. So the Powerwall is currently discharging, going into the home, and then if I turn the heater off, there'll be a 2-second delay, and then as you can see, it works itself out. The rate drops down from the house, and then any excess power from the solar then goes into the Powerwall, so that when again I turn on this heater, any other excess power that was being stored up when there was surplus solar then goes back into the home, and we don't need to touch the grid. You can see every now and again a tiny bit gets taken out until the battery realizes how much it needs to produce, and then it settles down, and then it just takes it out of the battery. The app's also useful because it can show me how much power is being put in the battery, how much is taken out. So anything below this line is being put in, anything above it is going out. Now the battery was flat this morning, so that's why not much has gone out of it, most of it's gone in. And I can show you, if I go to demand from the house, you can see there we had very high demand with there was lots of cooking, we were doing hoovering, using a couple of power tools as well. So the demand went very high, and if I put in the solar here, which is the yellow, you can see the solar wasn't able to make up for the demand of the house, so we didn't have any surplus to charge the battery. The battery was already at 0%, so because of that it wasn't able to power the house. But if the battery was full this morning, these peaks from the house would have been entirely supplied by the battery, so that wouldn't be an issue. That's the idea with this system. It means you don't need to take anything from the grid or get anything to the grid. You can use all your own solar power. That way you save money, because when you buy electricity from the grid, it's a lot more expensive than the money you get for supplying the energy to the grid. So this way it balances it out nicely. You can see here, if I turn off the other things, and you look at the grid, you can see periods here where we're absolutely off grid, and the only power we're getting is either from the Powerwall or it's from the solar voltaic system. So for safety reasons, currently the Tesla Powerwall can only provide us power when it has some kind of communication with the national grid. So if there's a power cut, we actually do lose power. Even though we're producing energy from the solar panels and we've got loads of power stored up in the battery, we can't actually use any of that energy, because the problem is if somebody's outside trying to fix the electric power line and we're generating electricity, we could be potentially sending some electricity to the grid, and if we're doing that and someone's working on the line, they could get electrocuted. So at the moment we can't run off-grid, but that's going to be installed at a later date. So when it's installed at a later date, basically all it'll be is it'll be a little box similar to this, probably a bit smaller than that, situated somewhere else in this cupboard or slightly further along in the other cupboard. So what it will do is when it detects a power cut, it will completely disconnect the mains electricity to the grid, and that means that it's safe for us to generate electricity and it won't leach out to the grid and injure anyone who's trying to repair the grid. So that means we can run off the solar panels and we can run off the battery as well. And if it's summertime, you know, we could go for weeks or months even running off grid, no problem. So that switch will be really helpful if there's any power cuts. Normally in the UK, power cuts aren't an issue. You maybe only get once a power cut for a couple of minutes, once a year, maybe every 2 or 3 years. But here in North Scotland, all the power lines are actually overhead. Even in the villages, we have cables going overhead to our houses. So the power cuts are quite a bit more common here, especially as we sometimes have wind gusts over 100 miles an hour. It does get really windy up here. We do get power outages maybe 2 or 3 times a year. So that'll be quite helpful, so we can keep our fridges and freezers going, because that's a major problem. Also, it allows us to heat the house better, because at the moment with the log burning stove, we can heat the hot water and we can heat the living room with a log burning stove. But if there's a power cut, we can't send that hot water around the radiator pipes. So when there's a power cut, you can keep one room hot, you can still have a hot shower, but you can't send the heat around the rest of the house. So the living room's nice and warm and the area near the living room is nice and warm, but without the radiator pump going, you can't heat up the entire house. And unfortunately, you can still heat up the hot water tank because of a thermal siphon that works, but I'll explain that more in a later part of the video. So the system I showed you earlier was the battery system on the Tesla Powerwall. This is the main electrics for the house, and the way that this works is we have something called a gateway. That is actually the brains of the Tesla battery. It measures all the power going in and out of the different systems, such as the house, the battery. It also measures the power coming in and out of the solar, and it figures out when the battery should be charging, when it should be discharging. It takes control of all that. It's connected to the internet, so we've got this here, providing internet connection. So that's how I can access the app. The data from the app is basically being taken off the internet, which is then fed in from this gateway. So the battery won't fully charge itself in the winter time, but come summertime we should still have a surplus, even though we're charging the battery up. We probably won't be able to completely deplete it during the day because our electric demands are not quite that high. So what we do is we use this thing here, and this particular one's called Immersion. And what this does is any surplus power that we have, we can then put into the hot water system. So what happens is once the Tesla Powerwall is 100% battery and we can't put any more power in that, what we do is we then put power into this then detects that and puts power into an immersion heater in our thermal store, and the thermal store heats up the hot water in the thermal store heats up using the waste electricity. So this dribbles in. It can either be a small amount if there's not much surplus power, or if there's a lot of surplus power we can dump huge amounts in, because we've got 2 immersion heaters. I think each one's about 2,000 or 3,000 watts. So we can put in anywhere between 4 and 6 kilowatts at a time, which with a 4 kilowatt solar system, we'll easily be able to dump all of the power into that. So this will heat the water up until it gets too hot. When the water gets too hot, it will then start sending it to the grid. So we'll not need to send it to the grid very often, and this means we won't need to heat the water as much. So this will save us on burning the wood. It'll also save us a bit on electricity costs, and also it should work quite well. Any excess power that we can't save in the battery go into the hot water system, and that hot water can be used for washing, for like dishes and things like that, or showers and baths. But the hot water can also be used for heating. So there's radiators, there's a wet radiator system in the whole house, and that can be used to heat the building as well. So there's several different ways that we can use that water once it's heated up. So the main aspect when it comes to heating the house is wood. So we need a wood store to look after the wood, keep it dry until we need it. So this is the wood store. It's built in mind that most of the weather comes from the west. So the western side of the wood store here is well protected. You can see all the faces here are sealed up. There's no gaps or anything. We've also got some old double glazed windows here to seal it. So when the wind blows from the west, rain or water can't get in. But it's very important that you can let air in so that there's ventilation. So because of that, the areas which aren't exposed to the west, we do have lots of gaps for air. So you can see here in the gaps in the rafters for air to get through. Also, all the other walls on the woodshed, apart from the wall which is alongside the garage, is actually made out of slatted wood like this, so there's really good airflow. It's important to have a good airflow because without it the wood will stay really damp and it could get quite mouldy, and then it wouldn't burn very well in the fire. Because the drier the wood, the more efficient it is, and it's really important to have very dry wood, because then you can really get high efficiency with your burn. You don't have to use as much wood. So the door we got here is actually really large. It's from an old shed, and the reason we wanted it really big is because it's easy to get things in and out. So we don't have to worry about space. You can see the size of it there. It also means that when it's decent dry weather, we can just open this door and it gets really good airflow. So this actually, as I say, mostly from the westerly direction, the wind. So the wind gets channeled between the garage and the little extension of the woodshed here, and the wind just really blows through really nice. Got really good airflow. And then if the rain comes, we can just close this and seal it off from the west. So inside the woodshed, we've got pallets to raise up the wood above the ground so that it doesn't sit on the concrete, just because if there is heavy rain, there's a chance water could seep underneath. That just keeps the wood dry. The main area is wood over here. This rounded logs tends to be wood that my parents have got from friends and family off trees. This might need a bit of seasoning, so might leave this to dry out for quite a while. We've got a little thing we can use to test the wood, see how wet it is and if it's dried out enough to be burnt. And then in here is the main part of the wood store. It goes a long way back. It's kind of hard to show from this because it's half full of wood at the moment. This goes the length of the garage basically. It goes all the way up to where you can probably see light coming through at the back. And this is where we get wood in. This is actually bought wood, so somebody else has dried it out. The rounded ones, I do believe my parents have got from friends and family or from the garden, and they're dry enough for them to burn now, so they're in this section. But this is the main part of the wood store, and generally if we fill it up completely to the entrance here, I'll just walk back so you can see it. If we fill it up to this entrance, that's normally a good winter supply of wood. But we do also have lots of other capacity back here. We can store more wood if needed. So if we ever have a really hard winter, we should have plenty of wood and we can store a lot more if we need it. And then lastly, another source of fuel for us is recycled paper. So my dad uses paper, he wets it, he adds some sawdust as well, because he gets a lot of sawdust from cutting wood and processing it. He then compacts it into squares using this special device here. It compacts the water out of the paper, so it gets nice and compressed and dries it slightly, but it's still quite wet even after you compacted it. So it sits here for a few weeks in the sun from the window. Once it's dry, that can be burnt on the fire, or he also uses it for insulation in one of his sheds. So I thought I'd show this quickly, just an example of how much recycled paper we're able to get. Now, paper is pretty much a waste product here in Scotland, so you can get it for free very easily. As you can see, loads of shredded paper, a whole wheelie bin full, and we can just process that, make it into bricks, and use it to heat the house. Or also, he's making insulation bricks from it, so we can insulate some of the sheds, and then the sheds keep the temperature better, and you can use that for vegetable storage or whatever else he uses the sheds for. Also helpful if you've got a shed and you don't want your tools to freeze or anything, if you've got batteries on the tools. So just use that as insulation, and also for heating the house by burning those bricks. So I feel the same when it comes to burning the logs. They're counted as a carbon neutral fuel source, because the trees, as they grow, they absorb carbon dioxide, they store the carbon up in their logs as the wood. So when you burn the wood, you're releasing that carbon, but that carbon was only absorbed in the last 20-30 years, so it's seen as a renewable source. It's not fossil fuels, so the net amount of carbon dioxide isn't going up. It's just recycling the existing carbon dioxide. So that's why wood burning is an eco source of fuel. You do have to sometimes worry about the emissions of the smoke and toxins from the smoke, but we've got quite an efficient log burning stove, and if you've got a good efficient stove, they're very clean burning. You don't get barely any smoke. It's just steam coming out the top. So what we have here is the log burning stove, and this is the main heating source for the whole house, also for the hot water as well. So this is able to burn wood, or it's also able to burn solid fuel such as coal. We always burn wood though, because we use the ash in the garden for fertilising the garden, so we don't want to use coal. And also coal is a fossil fuel, so if you're using coal then you're going to be releasing CO2 from fossil fuels. We want to be as carbon neutral as possible if we can. So this actually puts out 13.6 kilowatts into the hot water, and 9.5 kilowatts to the room, which is fine because this is quite a large room, but we do need to have the door open most of the time because that's an awful lot of heat going into a room. So we do have the door open when it's going, but the majority of the heat does go into the water system. We went for this stove because with this one it's actually surrounded with wood water on three sides. On the two sides there's water. I think above there's some water as well, and certainly the whole of the back there's water. The only bit that's not surrounded by water is the front here. So it's got two walls inside the frame. The outer wall and then the inner chamber, the gap between them is surrounded by water. So what happens is the water comes in from down here. It goes through the stove, and then it comes out at the higher section there. It then comes up the wall into the loft, and then across and into the hot water tank in the loft. So this system works quite well. It doesn't actually have a pump to pump the hot water into the tank. It works on a thermal siphon principle. So the way that works is when water gets hot, it's less dense than when it's cold. So it's got slight buoyancy to it. It works in the same way that hot air rises, and why hot air balloons work. So when the water is warm, it will rise to the highest point, and because it's about 3 meters higher than the lowest point, which is where it comes into the stove, that gives it quite a bit of a height that it can pull up by. So the water will go up there, and as it goes up there, it sucks and also pushes down the cold water, which then goes back into the stove. And with a 3 meter height, we can get quite a good flow going on it without the need to have any electrical pumps. And the main reason you need that is because if you had a power cut and you had this stove on and that hot water wasn't able to keep cycling, it could start boiling and then you could have an explosion. So it naturally recycles itself. It doesn't need a pump to go. So the water heats up the hot water tank, and from the hot water tank we can then run the radiators. So this is the main stove. As I say, it's quite a large one, puts out a lot of heat. We have it running most of the time in winter. It's thermostatically controlled as well. So there's actually a thermostat here, so you can choose the temperature of the water. There's a thermostat on the back of it, and that tells how hot the water is inside the actual casing of the stove. It doesn't know how hot it is in the tank, but it knows how hot the water is in the stove. So we can adjust this, and what it does is when it cools down, it opens the air vents more, lets more air in, heats it up, and then when it gets to a good temperature, it can close the air vents and then maintain that temperature. So we can adjust the valve there, this thermostat control for the water inside the actual stove. As I say, it doesn't affect the water on the hot water tank. And we also have a fan on the top. This fan is just powered by the temperature difference between the bottom of the plate and the top of the plate. So it's a small electrical fan. You can see there's little thermocouple, this little unit in here which generates the power through the difference. It doesn't run too fast in this stove because it's actually designed for higher temperatures, and because this is a water cooled stove, it doesn't get too hot. I can put my hand on it there and it's not going to burn me straight away, but it's still very hot to touch, probably about 80 degrees. So it runs quite slow, but the idea of that is to blow hot air out into the hallway. Also with the stove, you can see the chimney is not insulated until it gets close to the ceiling. So all the hot air that comes out the top of the exhaust from the stove, a lot of the heat can go back into the room. It is quite efficient. I think it's about 80%, so the majority of the heat is going into the water and into the room, and then any excess heat, any heat which is inefficiently put into the flue system, comes up here, gets leached out, and then by the time it's up here it's a lot cooler. It's still really hot, and so it needs to be insulated so it doesn't burn the roof because there's wood up there, and it also could damage the plasterwork and the paintwork. So this insulated as soon as it gets up to that height and until it leaves the actual roof. Now you could maybe collect some more heat from the chimney. You're still losing quite a lot of heat out the chimney. As I say, it's probably only about 20% heat loss, maybe a bit less. And if you do take too much heat out of the chimney, then you have problems where there's not enough airflow, and then you need to start having fans for it. So next I'll go up into the loft and I'll show you the real kind of hearts and guts of the system, where all the water collects and also where some of the photovoltaics come in. So now up here in the loft, the lighting isn't great up here because it's not anywhere that people regularly go. So there's no permanent lighting system, so it kind of torches and ad hoc lighting in half of it. But here's the inverter. So what basically happens is, if I show you up here, this is where the voltage comes in, or the power comes in from these solar panels. It's at quite a low voltage, comes in, and it's at direct current, so DC current comes down through a couple of breakers, and then it comes into the alternator. So what this basically does is it transfers the direct current into alternating current, which can be used by the house. So this is the main unit we have, and this changes it into, as I say, the alternating current, which then can be used by any appliances in the house, or can be put into the battery system of the Powerwall. And so this is the real kind of guts of the solar system. This is what produces the power. The solar panels produce the electricity, but that type of electricity can't be used by any appliances. So this is a thing that turns it into usable alternating current power. So this just sits up here, makes a slight hum, but generally doesn't make much noise, and sits up in the loft. So this here is the real guts of the system. This is all the basically what you should say, like the wet system. It's basically all the heating pipes, plumbing and everything like that. The main part of it is up here, is the thermal mass storage system. You can see it's quite a size. I think it's about 140 litres. It's about 7 foot tall, something like that. And what it does is it takes in all the different heat sources and it distributes them evenly around the house, and I'll show you how it does that. So if I take you around this side, so this is the main ins and outs of the solar thermal tank. The hot water from the stove comes in here, heats up the water in the hot water tank, and then comes back out. The hot water from the stove is then stored and used when it's needed. So it takes a while to heat up, but once it's heated up, it's got a huge amount of power. You can use a lot of that heat before it runs out. This is a decent size. And so this can be used to heat the radiator system or the hot water in the hot water taps. So you can use this for showering or washing up, or it can be used for the radiators. When it's used for the radiators, it probably only heats for about half an hour or an hour. But when it's used to heat the showers or something, it lasts a lot longer. Generally showers and things don't need as much hot water as a radiator system. So this takes power from several different inputs. As I say, that silver one on the right hand side is for the hot water from the stove. Down here there are two immersion heaters. These are the two black round things there. The immersion heaters run off the electrical system. So the excess power from the electrical system from the solar panels is used to heat the water via that. So that's the second way it heats up. And the third way is from the solar thermal that I showed you outside earlier. And I'll just show you now where that is. So the solar thermal panel is on the outside, has the two inlets coming through these two tubes here. They come down and into a control box. Now this control box is here to make sure that the temperature, this is here to make sure that the pump doesn't operate unless the temperature from the panel is warmer than the temperature in the hot water tank. So what would happen then is, if the temperature of the hot water tank was warmer than the temperature of the panel outside, you'd have to be cooling down the hot water tank and heating up the panel. So once the panel is hotter than the hot water tank is, it'll run the pump and send the heat from that's been heated by the sunshine into the hot water tank, and that just goes in via these pipes here. And that's another way that this tank can be heated up. Got three different inputs for this tank. It's got the heat coming from the log burning stove. It's also got the heat coming from the excess power from the solar system, and it's got heat coming from the solar thermal from the sunshine heating up the panel on the outside. So several ways it can take in heat. So there's three ways in. The two ways it can take out the heat is either hot water for your hot water system, or hot water for your radiator pipes. And there's several different compressor valves and overflow systems and tanks like that. I won't go through all of them as they're quite complicated and I'm not a trained plumber. But that's basically the ins and out of the heating system. It's quite complicated, lots of different aspects to it, but it does mean that you can get heat from all different sources. So if you run out of wood, you've still got solar. If you don't have solar, you can use wood. But the vast majority in the winter is from the burning of the logs to heat the stove and heat the water. And when it comes to summer, pretty much the solar panels do most of the work, and we don't need to burn any wood unless it's a particularly cold, cloudy week or something like that. So that's it for this this video. I think, as I say, you can see in the garden, most of the food is produced on site, is eaten there. Very few vegetables need to be brought in, apart from maybe bananas or oranges, things that are more tropical. With the heating system, not much power at all needs to be taken in from the grid. In summertime, we're actually exporting a lot of excess power to the grid. That's helping to offset some of the power that we need to take in from the grid during the winter months when there's not enough solar to make up for the heating demands. So over the year, it is generally about carbon neutral. There's probably a little bit carbon positive still, but we've not done the exact calculations, so it could be carbon negative, we don't really know. But the household as a whole, I reckon, is around carbon neutral.